I hope we don't have this for Burl.
Oh yeah, you don't care if I have it.
Oh, I didn't get that.
Am I on the air? I'm on the air, right? Yeah.
All right, good morning, everyone. As you can tell, we've had a few technical difficulties this morning, and I can't take any blame or any credit for getting them under control again. I'm Joanne Bundy, and on behalf of the Planning Committee, I welcome you to the bucket courses this morning. I believe that we have the T-coil working, so for those of you who have hearing aids that accommodate the T-coil, you might try that to see if it's working for you this morning. Does it work? Okay, very good. That's
Mine is. I have a buzz.
We have a request, of course, to turn your cell phones off. And I had a request also to tell you at the end of the program to turn them on again. But I'll let you take care of that yourself. I want to tell you about a schedule change that we have had. Next week was supposed to be Dr. J.R. Paulson, and he has had to rearrange his schedule, and he will be October 16th. And Pearl Kleinfelder, who was scheduled at that time, was kind enough to do the class next week. So we'll still get everybody in, but Earl will be next week, and JR will be October 16th. So you might make a note of that, and perhaps Jim can send you a reminder, an email, too, that there is a difference. But this morning, we have a new area which we have not touched before, which is the space program. And we are fortunate enough to have the design leader, am I getting this right? For the Apollo mission. And I think you are not only going to have an entertaining day, but we might even learn something this morning. So Jim Kottmeier, please welcome him.
Now, I should be on the air. Can you hear me all right?
Yes.
Pardon me. The title of this, I've titled as Footprints on the Moon. I am Jim Kottmeier, by the way. I'm not a professor. You're used to seeing professors up here. I do profess, and I have professed, but I'm not a professional, so I can't call myself a professor. Footprints on the Moon is the title that I gave this in 1965 when I gave a very abbreviated version of this to some junior high kids in Twin Cities. And it started out, before you graduate from high school, man will have landed on the moon. Well, we know that that did happen, and I'm going to try to tell you a little bit about my involvement with that and my journey with the Apollo program and how I got there, and a little bit about manned spaceflight and how that evolved. I was going to entitle this The Origin of the Nerd, because this was the era of pocket protectors. I don't know if you all remember pocket protectors. They were a little plastic device that you put in your white shirt with your black tie, narrow black tie, and black slacks. It kept ink and pencils and stuff in one spot and kept it out of your shirt. In there you had probably 2 mechanical pencils, not real pencils, like you're used to, and you probably didn't have a pen unless you were a manager. You had a slide rule, the precursor to the calculator, and you probably had a scale, not a ruler, but a scale. The difference is the scale had different types of measurements other than inches or millimeters, which most of us had a ruler in high school and our little pencil kit that had that. That wasn't it. Nonetheless, Footprints on the Moon, the iconic footprint on the moon from Neil Armstrong's boot. Pretty cool, actually. We could actually go all the way back, and I edited this out because it starts with the ancients who studied astronomy and mathematics and those two things coupled up essentially is the space program in much elaboration. We owe a lot. In the 60s this happened. Now most of this. Let's go back to January of 44, because that's when Wernher von Braun, who is the brain of rocket science, he really was a rocket scientist, developed a guided missile. Prior to that, all the warheads, you just fired them and hope they landed somewhere near a target. You can actually control his missile. You can see there alcohol and water mixture below, above that, guiding beams and things like that. And it's over in there. Automatic control gyros, critical to control anything, and we'll get to that a little bit in a minute too about gyros. Nonetheless, Hitler decided to gave America two things. He gave us the interstate highway system and the space program. He didn't know he did that, but he did. And our paranoia pushed those things to the forefront because we were deathly afraid of the Russians. You have to remember, put this in some kind of socioeconomic context. The Cold War predictably forced us to do things. Hitler gives Wernher von Braun the blank check, essentially, to Russia's A4V2 project. Luckily, he did that too late, and we the Allies and the Russians, we squeezed the Russians and defeated them before they could get this running effectively. Had they done that, I think we'd have been a different world, truthfully. So in May of 45, the war's over. Wernher von Braun and his staff, critical there, surrendered, also critical to the United States. They didn't surrender to the Russians, which they could have. Russia and the United States essentially split the brain trust of German science. That's oversimplification. Wernher von Braun is the guy with his arm in a cast. We don't know how that happened. Don't care. Nonetheless, this guy he was to rocket science what our friend from Grinnell here was to the microchip. August of 55, still in the mid-50s, Lockheed releases the U-2. U-2, or black, what's the name?
Blackbird.
Blackbird, right. Released from its Skunk Works. Skunk Works is a vernacular for any top secret military project area. Also called Secret Squirrel, many other vernacular names. This thing flew at the edge of what we considered space at the time, 70,000 feet and at least Mach 2. Now those are the released numbers. I suspect there are other numbers. If the government releases a statistic, it's a safe-sided number, you can bet on it. That little device there I'll talk about in a minute, that's an antenna, and we'll get to that. Nonetheless, this guy flew it at the edge of our gravitational system. And it was, ironically, it was shot down by the Russians. You may remember that. Ray Powers flying over Russia, flight out of Ankara, Turkey, flew over Russia, they fired a missile, hit him, and shot him down. They didn't think they could be hit at that altitude.
I'm wrong, that's not the Blackbird. The Blackbird is the rocket they had later on that could outrun their rockets.
Oh, Jack is correcting himself and me as he led me astray once again. Blackbird is not the name of this. It's Black something though, and I can't remember what it's called. Nonetheless, they shot it down. This was run by the CIA. President Eisenhower at the time did not know anything about this, ironically. He was politically and publicly embarrassed because the Russians said, "We got your spy plane." He said, "No, you don't. We don't have a spy plane." They said, "Here's the pilot, here's the plane." So Ike was in deep weeds politically, and the CIA and the executive branch of the government were at odds politically. Let's just leave it at that. So in '58, I start my drafting career at Jefferson High School in Cedar Rapids, Iowa. My advisor in junior high school, turns out, was my cousin, my cousin's husband, actually. He advised me because I'd taken aptitude tests and all that Iowa test stuff that they used to do when Iowa was really good at education. And I showed an aptitude for spatial things and geometry and things like that. So he suggested I try drafting. And I tried it, he said, try it in summer school, and if you don't like it, you haven't wasted time in school. So I tried it in summer school, which I always thought was for the slow.
Yeah.
I was a little insulted by that. Turns out there are two types of people in summer school, the slow and people who wanted extra stuff. So I took 3 summers of summer school drafting in 3 years, 2 semesters, 6 credits, 6 semesters of drafting in school, 9 total semesters of drafting. They didn't have 9 semesters of drafting in the public school system. Luckily, the drafting instructor, who was a terrific young man, created programs for about 3 of us that were pushing past the curriculum. And he challenged us to do a lot of things, most of which were mechanical drafting in those days, because electronics had not really, was not really prevalent. Electrical was, but electronics weren't. Printed circuits were just evolving, so all of that was still happening. Nonetheless, we had all these great courses and a great guy, and he got us through that, and I took that, all the geometry I could take, all the physics that they offered, did not take chemistry. The chart of elements freaked me out, and I ran out of that room. That was like a foreign language, and I didn't need another one. I took Latin. So then I had college prep was the track you were on in those days. Now it's AP courses. And typing. You had to take typing on a typewriter, mechanical typewriter.
Yeah.
Believe it or not. And it was mostly filled with young women who wanted to be secretaries or stenographers, and a few geeks like me. So in May of '61, when I'm a junior in high school, President Kennedy throws down the gauntlet in a speech before both houses of Congress and predominantly to the Soviet Union. He was not speaking, believe it or not, as much to us as he was to the Soviets, because remember, there are bitter rivals in this. He says, before the end of this decade, the 60s, we will put a man on the moon and bring him safely to Earth. Underline returning safely to Earth, because that is a very critical part of the space program and a very difficult part of the space program, particularly that word, safely. That means he's got to come back in one piece, healthy, speaking English, all of that. So there I am. See, I used to have hair. This is for my granddaughter, so she knows that I had hair at one time. In June of '62, I graduate from Jefferson High School, and I go to work at Collins Radio in Cedar Rapids, Iowa, as a draftsman. There are 3 levels of draftsman in this era: detail draftsman, layout draftsman, and design draftsman. Detail is small functional things which you can't see, like this. Layout is a little bit more big picture stuff, and design is conceptual or very big picture stuff. Collins Radio was a fairly good place to work. Paid well, seemed stable, all of that. Well, real world lesson number 1. Collins loses a bid and I get laid off. Now I'm 19 years old. This is actually not Cedar Rapids. They didn't wear hats like that in Cedar Rapids. And coffee. We didn't have free coffee donuts either. Nonetheless, I'm laid off. I'm 19 years old, I'm laid off. I don't know what's going on. So I go back to work, believe it or not, because resumes are flooding that whole region in eastern Iowa for jobs like mine. And being single, I was not given the opportunities, nor should I have been given the opportunities that were given to married people who had children, who had obligations. My obligations were minimal. So a lot of the jobs went to older married people who had families. So I go back to work at a gas station that I worked at in high school, and actually where we pump gas, wash windows, and check your oil. Wore a little cap, white. Yeah. Origin of the nerds. Nonetheless, I'm working at this high school place, and I send resumes out. I really wanted to work at the Amanas, Amana Refrigeration, I think it was called in those days, and didn't get any action. So flood resumes out, nothing's happening. In August of '64, a guy from Minneapolis comes down from Strong Engineering. Now, this is Minneapolis. In the winter, not in July. This is Mary Tyler Moore. She wasn't there in August of '64. I just like that picture. Nonetheless, this guy comes down from Minneapolis and talks to two of us that were laid off at Collins. Why and how he found me, I have no clue. The stars, the moon, phases of the moon, who knows? Nonetheless, he offers me a job to come to Minneapolis. I had no idea where Minneapolis was, because living in Cedar Rapids, our view was to Chicago. Because that's where the railroads went, that's where the highways went. They had professional sports. That was the big city if you were going to leave Cedar Rapids and go to the big city. Minneapolis, who the hell knew where that was? It's up there somewhere. I mean, I knew where it was geographically. I knew nothing about it. Well, it turned out to be a pretty good place to go, actually. And Strom Engineering is a contract engineering company. And by that, I mean they would hire technical people only. Engineers, designers, draftsmen, tech writers, publication writers that wrote technical bulletins and stuff like that. And they would job them, contract them into places that needed temporary short-term contract help to finish a contract, so that company then didn't have to hire and pay full-time benefits to people. So it's like a Kelly girl in a sense, but only in technical businesses. So that's me, actually. No, it's not. So I go to Honeywell Aeronautics, Honeywell Aero, as it's known. And Honeywell Aero built a thermostat, well, Aero did. Honeywell built the infamous round thermostat that many of you have had in your house.
Oh, yeah.
Everybody had one. Made the company. Honeywell Regulator was its original name. Honeywell Aero was a division. And predominantly they made gyros. These little devices here that tell you when you're in either water or space, air, whether you're going pitch, yaw, or roll. Those are the three dimensions in space. Pitch is in yaw, horizontal axis, vertical axis. Pitch, yaw, and roll. There, it's kind of semi-diagram for you there. That is a typical drafting room. I couldn't, of course, take pictures even if I had wanted to, because everything in Honeywell Aero was top secret. There were, believe me, you didn't go in and out of there with a camera. But that's a typical drafting room. These are drafting machines, they're called, and they bend there, and there, the 3-point pivots. You just line that up and it will, you move it all over your board and it remains parallel to the bottom or vertical, parallel to the edge. Or you put it at angles that you wanted at 15, 25, whatever. And it would be a constant. I, of course, by the same design that I'm on this side of the room, had my drafting machine over here because I'm left-handed. And I've forced some of you to change your seating position, which I'm proud of. Nonetheless, that's pretty much how it looked. And you can see people, by and large, could stand. The board was hydraulic. You could raise, push down on a clutch kind of thing and it would raise. Or you could put it down and sit, or you could do any combination of it. You eventually will develop a back problem from doing this, which I did. But it didn't keep me out of the Army. Never understood that. So, there I was at Honeywell. First I go to Honeywell, and I'm in what's called the ECO group, Engineering Change Order, the lowest form of drafting. This is where the semi-literates go. And I don't know why I was there. They probably knew why I was there, but I didn't. I was only there 6 days. What I liked about it, two things. One is the boss of that group was terrific, terrific man. The other was there was a Danish woman that worked there. That was my first experience with European women. And it was good. My boss left after a week. I'm there a week, and my boss goes across the street to Breedy Building, which is just the name of the street. Anyway, so all I had left was the Danish woman, which isn't bad. But then on Monday, so I'm there 6 days, and my boss, former boss, is now across the street, calls me and says, "We want you to come across the street." And that was a big deal to go across the street, because that's where Aero was. So I go across the street. I have no clue what's going to happen. Much like my trip to Minneapolis, I had no clue. What's the worst that can happen? That was always been my mantra. So I go there and I'm working on Apollo. I didn't even know what Apollo was when I went across the street. So Apollo didn't exist. It didn't. Conceptually it existed, but it wasn't material. Before you think outside the box, you need a box. We didn't have a box. We had nothing. We literally had this blackboard would have been blank in our group of thinking. And this cartoon I always liked. There's got formulas here and there, and it says then a miracle occurs. We kind of live by that theory. And the guy says, I think you should be more explicit in step 2. At this stage, we weren't being very explicit. We really weren't. This is very conceptual. What do we need to do? And that I just like because I love those kind of devices that are, what are they called?
Blackboard?
What?
What are you talking about, the blackboard?
Oh, the triangle,
I figured that,
Oh, those.
whatever.
whatever they're called.
Can't think what it's called. What is it?
Optical illusion.
Optical illusion, thank you. How come I can't make this thing go forward? No, geez, no. No, announce the restarting the program. I'm gonna be obstinate. I guess I am gonna restart the program. Jeez. Boo. This is where, if you're at the drive-in, this is when you turn your lights on and honk your horn. See, some of you know what a drive-in is. That's pretty cool, I think. Anyway, so we're at Honeywell Aero, and I'm, believe it or not, I am a real rookie. I'm still, by this time I'm 20 years old, and I've been given an opportunity that I have not even a clue how great of an opportunity this would be. And it's mostly a retrospect that you see how big of a deal this was, at least to me. I didn't realize what we were doing. And sometimes I work best when I don't know what I'm doing. The concept of space travel hadn't occurred except in like comic books and Captain Marvel and those kind of things. So, and believe it or not, that's a lot of what we went by. I know you think this is all rocket science. But there was no rocket. I mean, the rocket science was, I can't talk and do this at the same time. Where did I go, Jack?
Slideshow.
Where is it? Slideshow. What did I do? What did I do?
You should go to slideshow.
Shouldn't have done that, should I? Where's slideshow? I can't even see it. Too close to it.
To your right, slideshow.
Am I right?
Slideshow.
Look on the screen.
And don't say it's the hand I write
Slideshow.
on, where?
Right under Power Bucket.
Right under bucket. There, that's it.
Where it says slideshow there?
Yeah.
That's the one.
All right.
It's from current slide. Go from current slide.
Second current slide.
To your left.
Left.
That's it.
And this is how we designed Apollo. One person doesn't design anything, believe me. So, from in August of '64 till the end of the year, we conceptualized it, and by that, well, I mean it was blue sky stuff. In January, we had to get down to make this baby real. SCS is the vernacular for the Stabilization Control System, and that's what we built at Honeywell. It's essentially the guidance system or the steering wheel for two pieces of the spaceship. The Apollo Command Module, which is the part the three guys sit in at launch. It's on the very top of the rocket. And LEM, the Lunar Excursion Module, which is the little device that goes down to the moon. And the guy steps down from the ladder, puts his boot on the ground, and makes the iconic footprint. They climb back up the ladder, blast off the moon, back to the spaceship, dock, and they crawl through a little tunnel, get in the big thing, throw the LEM away, literally. So, we had to figure out what is the guidance system? What do we need these things to do? How do we guide something in space? No friction, no resistance, just space. Lots of it. So we need, what do we need them to do? How many circuits do we have, can we have physically? The physical strength of these things, both of the circuits and the package, the whole thing. Will it fit in our allotted space, and can it be built? Key phrases. Will it fit we had at Honeywell out in the shop, we had a we had an actual size Apollo command module made out of fiberglass, I think. But nonetheless, it was the actual size of the spaceship. We went out, you could sit in it and make whirring noises like you were a little kid driving a Tonka truck around. Nonetheless, we knew how much space we had in that, and I'll show you the later slide how much space we wind up with. It ain't much, as you can imagine. This thing, this Apollo command module is little. So the phrase is, if you can design it, we can build it. That's what the model shop said. Well, and the model shop was who was going to build this, because this was not a production run.
Yeah.
The key to whether it worked or not was to put it on what's called the shake table. Shake table is this kind of a device. This isn't it, but it's a similar thing, which is bolted or welded or cemented to the floor, concreted to the floor, Jack, sorry. And it shakes in all dimensions, vertically, horizontally, and everything. Just shakes the bejesus out of things. So you weld your device here. Have you seen a page shaker like Ace Hardware?
Yeah.
It's like 15 times that. It's unbelievable. There's another thing I'll tell you about in a minute, but that's kind of fun. Anyway, you shake it here. We put electricity in here, and you bang electricity out there. Throw the switch, this thing begins to shake like you can't imagine. And our little device lights up like Firefly convention. You ain't supposed to do that. All these electrical circuits were arcing. And little sparks were everywhere. So I look at the guy at the head of the model shop and I said, apparently you can't build it. So that didn't set too well with him. I said, so we had a little bit to do and they had a lot to do, because what they were losing, or what caused that, was the tolerance, and we'll get to that in a minute. Tolerance is the amount of imprecision you're allowed. I don't know how to say that better. If I tell you I want an 1/8 inch diameter hole, plus or minus 5/10,000ths, and an 1/8 inch is 0.125, is it not? That means that hole can be 130 or 120 at the outside. If this one tolerance goes this way and this tolerance goes that way, we needed this much space in between to keep it from arcing electrically. So that's what that's about. Anyway, back to the drawing board, literally. So here we are again, same scene. You saw that before. So we're trucking along, and this is early '66, January, February, March of '66. There's a panic meeting we had because Gemini, which was currently in space, Gemini 8, in fact, was in space in March, started tumbling wildly at 17,500 miles an hour, which sounds dramatic, but in space that's all relative.
Yeah.
And it doesn't, there's no gravity, so you're not getting dizzy or all that stuff. Nonetheless, it shouldn't be doing it. Armstrong, Neil, some of you know him by his first name, decided the problem had to be a stuck thruster. Now, we'll get to that later too. There are 16 thrusters on the command module, and they are the things that control it. If you want to go left, you fire that one and it scoots you over to the left a little bit. And you go right, you fire that one and it pushes you that way. And you have to fire this one to stop you, because if you just go and it pushes you, you'll just keep going. Well, eventually you might stop, but you'll be way off course. So they started purposefully firing the thrusters one at a time, just to make sure what was going on. Number 8 did not respond. Aha, pretty good. I told you, these guys are smart. Why? That's the question. The deduction was pretty obvious, I think. The question was why. And we had that question because we were essentially designing the same kind of a system. Problem, it turns out, was McDonnell Douglas's, who built Gemini. North American Rockwell built, or was the prime contractor on Apollo. Well, when you have a device here, like this cable comes off and goes down there, well, the cable came off, a little burr on a aluminum edge of this frame. And the wire had rubbed on it, and rubbed on it, and rubbed on it, and rubbed on it, until it rubbed through the insulation, arced into the frame. That gave it the signal to open. It's like throwing the switch. And so then we had to make sure we had our edges covered. So, in March of '66, we do final test and we release it to production. And production, in this case, was the model shop because we only had 60 total units, 30 for the command module and 30 for LIM. Command module and LIM had the same logic and control devices because you didn't want them having to think about stuff once they learned it, that there was a difference when they crawled up into the LIM module, lunar module. It wanted to feel the same and kind of be the same. And if you know how it works, use it. You know, don't create something new just for the heck of it. So, here, let me back. I don't know if I can back up. I'm not going to try. From August to October, I'm contracted. I'm done at Honeywell Aero. You know, we're done designing Apollo. I get contracted, ironically, back to Collins Radio in Cedar Rapids, Iowa. Very strange. The world is very strange. And a guy that I don't even know comes up and says, "Kottmeier, do you have your drums here?" I said, "No, they're in Minneapolis." He said, "Well, get them. We got a recording. We got to do it." So then I wind up playing with this band that has a record out. Who knows where the world's going? Well, then my mom calls me and said, "Hey, we got a letter from Selective Service. Do you think we should open it?" And of course it said, "Greetings, your friends and neighbors have elected you to represent them
Your friends.
in the Army." At 66. Remember, 66. Yeah. Well, that's 66, 7, and 8. Worst years of the Vietnam War. I'm sure Jim will get into this. For casualties. Scared, you know what? Sphincter check plus. Luckily, I get to keep my top secret clearance. I had a top secret clearance to work on Apollo. Don't ask me how. I think you get those if you really don't care a lot about the secret part. And I don't. I saw things I probably should care about, but don't. So I get a top secret clearance, and there's only 3 levels: secret, and top secret crypto. Crypto meant you knew the code, and you could have the keys to the switch for the red button. I don't want that.
No thanks.
And they knew I didn't want that. I didn't even want this, but you get it. Goes with the turf. So the top secret clearance comes in real handy. I, for that reason alone, believe I was never sent into combat. I was, however, at United States Strike Command in Florida at MacDill Air Force Base, a Joint Forces base in Tampa, in St. Petersburg, actually. And I worked for an Air Force colonel, and we did secret stuff. I can't tell you what it was. There's actually a plan to end the war in Vietnam. Ironically, the 6-day war broke out in the Mediterranean, and they scrubbed the whole thing. It gave us 6 weeks to declassify it. We could have done it in a couple days. So my buddy from Chicago and I made a round of Tampa, St. Pete. So I find out, ironically, in 68, not, even worse than 66. 68 is Tet Offensive, riots in the United States like crazy. Really bad time in American history, I think. I find out you can get out 90 days early, up to 90 days early, if you get accepted. And I go, I want one of those. So I get accepted to University of Minnesota. Some of you probably know I went there. I tout that at every available opportunity. Because I think they gave me a great education, and I think it got me out of the Army. There's 2 reasons I like it. I had a good tour in the Army, and there's some stuff up here that alludes to that, and it was fun, but I'm glad it's over, and I'm glad I didn't have to go to Vietnam, and I feel very badly for those guys that either didn't come back or came back horizontally or came back with all kinds of illnesses. So this is a good place to take a break. Don't forget to tip your waiters and waitresses. And we'll see you in 5 or 10 minutes.
We will continue with our Apollo mission this morning. Jim Kottmeier.
Thank you for that thunderous applause. There was no applause. Okay. Manned space flights. We're going to get into the meat of the issue now. The first one you saw was the U-2 plane, the flag, whatever it was. Then we decided we're going to throw some humans up there, and you're thinking it was John Glenn. No, it was Ham. Ham was our first astronaut. Isn't he cute? See, he's got little thingies here. He looks pretty cocky in there, doesn't he? I think he has an attitude, but he's got little electronic devices hooked up to him. He's got a little, like, I would equate it to a car seat for a child. Because the seats in spacecraft are made for humans, adults, and he isn't, although he's probably smarter than some employees I've had. Nonetheless, he's hooked up because they check in flight, of course, and pre-flight, they check all of your physiological things, heartbeat, pulse, sweat, I can't even think of them all, but all of the physiological attributes that humans have, they check that all the time. Astronauts were the pilots of our manned spacecraft. That was a term that didn't exist until this program. There were 16 in the first class. One was a Marine pilot, most were West Point grads. Most were grad school grads and went to places like MIT, Caltech, Berkeley, Purdue, schools that had terrific engineering, because most of them were engineers. Several of them actually visited our shop in Minnesota at Honeywell. I don't know who they were, because nobody knew them then. They were just guys. They were just pilots. I think you gotta be nuts to be a test pilot anyway.
Yeah.
To fly something that's never been flown before and take it to its maximums, or maybe past its maximums. But to sit on top of a rocket and be thrown into space is, I think, a little scarier. Nonetheless, these guys were them. And there's Ham, who led these other guys, John Glenn, you may recognize. Not a photo, obviously, when he was 20. Those were the Mercury program. Mercury was program 1, Gemini was program 2, Apollo was program 3 of the space program. These guys were the Mercury guys. One guy, either no orbit or low Earth orbit, not really space. Gemini did everything it needed to do to make Apollo work. And there were more guys, of course, because there's 2 in each flight now. Gemini means 2 of us are twins. They were doing all the dry run for the Apollo moon landing except land on the moon. They did spacewalks, which turned out to be a critical part of the space program, being able to do, it's called EVA, extravehicular activities. And they literally go out of the spaceship in their space suit, hopefully sealed tighter than a drum, and they're out in space, cold, hot, vacuum, all kinds of bad things out there. But they did things like docking and separation. The way they did that, because there was only one part to their spaceship, they'd send up a Gemini mission. 2 days later, they sent another one up. And as they orbit, they lock up or sync up, and they would dock. And they're going, remember, like 17,000 miles an hour. Pardon me. But it's all relative, because the guy next to you is going 17,000 miles an hour. So they're going along like this, and they're inching closer. It's a little like you've seen pictures probably of a jet refueling, a tanker refueling a jet. Same premise. A little more exacting, but same premise. So anyway, they dock and they separate. Also kind of a key point. You have to be able to cleanly separate, not hang on. It's got all of the connectors have to come clean. So that was important. And then re-entry, critical. Again, I keep re-emphasizing that because it was a difficult part of our thinking. Climax of the manned moon missions, Apollo. There were 20 budgeted missions in the plan. Number 1, saddest story of all. It's on the launch pad at Cape Kennedy, Cape Canaveral at the time. On top of this huge rocket, there's a little command module. All of the stuff is there, completely as it would be if you hit the launch button. Gene Krantz, who was mission control, and maybe some of you remember that name, and he was in charge of mission control. He was the commander of the space program on the ground. He got into a political dispute with the Department of Defense, with the Pentagon, about how this test would be run. Gene wanted the door shut, or the doors open, I mean, the door, there's only one door, the door to the spacecraft open. And they're just gonna run through all the system tests, make sure all the wires are, you have continuity, you have a good system. And then they would get out and they'd go back, and then later they'd actually climb in and launch this baby. Well, the DOD guy, Department of Defense guy, said, we're gonna seal the door just like it's a real test. So they seal the door, they start pumping oxygen into the spacecraft, the command module, and they have a spark. And sparks and oxygen are not a good mix, particularly oxygen in high densities like that. And boom, they have a fire, almost immediately have a fire. The doors are sealed shut. You can, like you've seen movies where they turn the thing, it's kind of like that, and open it. The problem is that the fire is consuming the oxygen and making a vacuum. And the pressure from outside is just mashing that door shut. They can't get it open, they're getting weaker, boom, they succumb. 3 are dead. Was shining moment in our space program, listening rocket, blah, blah, blah. Bad, very bad. So then 2 through 6 did system test flights, but were unmanned. That means all their control was done from mission control on the ground. There were no people in the spaceship. But they did a lot of things in high orbit and in deep space. 7 through 10, 7, 8, 9, 10 were all manned and did lunar orbit. Well, you know what lunar orbit is? That's when they literally went around the backside of the moon. You may remember, if you used to listen to this stuff from Walter Cronkite or whoever, that when they go on the dark side of the moon, or the backside of the moon, we lose communication. It's a little bit of a tenuous couple of minutes. It's not real long, but if you don't know what's happening, it can seem very long. 11 was the first man on the moon. We all remember that, Neil Armstrong. Summer of '69. I was outside at that time. You could actually see the moon in the sky, and I'm listening to radio, and I think, it's hard to imagine. There's a guy up there. A guy from America. It's up there. 2 guys. Weird. Well, it's bizarre to think that this actually happened. In fact, a lot of people don't. 12, 14, 15, 16, 17, those went to the moon's surface, as did 11, and collected data, rocks, dirt, dust, photographs, lots of readings of things, gases, and whatever they could test. I don't even know what all they tested. Here's some trivia for you. I think I have time for this. To transport the rocks back to Earth, which is not a bad ride until you hit the Earth's atmosphere, then it starts to go crazy on you because of the friction. And the spaceship rattles, and you've seen pictures of that, and the fire comes off the front of it. And those little ceramic plates are heating up to a phenomenal temperature. And the machine is fighting re-entry. So to ship the rocks back, they didn't want to break them or pulverize them, which it might have done. They put them in water. And the water they selected, trivia, is from Hot Springs, Arkansas. Tested to be the purest water they could find. Ironically, the water from Hot Springs and the water from Baden-Baden, Germany, from their hot springs, was like chemically identical. So there you go, 2 pieces of trivia. Both of which together don't make one good piece. 13, we know about orbits the moon, has a real problem. If you've seen the movie Apollo 13, the movie is incredibly accurate. It's based on a book by Lovell, I believe it's Lovell, who was one of the 3 astronauts in that ship. They run out of, I think it's oxygen. They go into the lunar module and try to set their ground control in Florida. helps them kludge together, and kludge is an expression from, at least from my experience in this era, which means that you take things that aren't supposed to be together and make them work. And that's what they did, and our ever-popular duct tape was part of that solution. In the movie, they made kind of a big deal that they were in the lunar module as a lifeboat. That was always the plan, by the way, and that's why it was so exactingly like the command module in its electronics. So anyway, by the time 17 had gone to the moon, picked up some rocks and done its thing, people were losing interest, politicians were upset with space program, they didn't see a purpose in it, and so they canceled the last 3 missions. And the astronauts, of course, got reassigned to do something else. Some of those guys there. Here's Saturn V. Got to do a couple minutes on this guy, because without this, there is no Apollo program. It is an unbelievable piece of machinery. Almost 37 stories tall. 5 enormous engines. Back here, you can't quite see it. There's 5 very up to stage 1, stage 2, stage 3. Stage 1 burns kerosene, liquid oxygen, 7.5 million pounds of thrust. I have no idea how to relate that to you. Nothing you know has 1 million pounds of thrust. Nothing you know has, I don't know how much, what does a car have for thrust? A jet, what does a jet have for thrust on takeoff?
I don't know.
Not a lot, not anything approximating that.
No.
Only burns for 2.5 minutes. Not very long, goes 40 miles straight up. Now, when you watch it on TV, it looks like it's bending. Well, part of that is gravitational pull, and part of it is the Earth is moving as it's moving. But it's pretty much going straight up. It's going straight up as far as resisting gravity. Then it, boom, it separates, actually explodes apart, falls into the Atlantic Ocean. I don't know if they picked those up or if they left them as reefs. Stage 2 also burns liquid hydrogen and liquid oxygen. Burn 1 million pounds of thrust, because now you've got a tremendous amount of momentum already going. Your acceleration is huge, so you don't need as much thrust. You're not fighting gravity nearly as badly now. Only burns for 6 minutes, and it's huge. It's that. I mean, and I'll show you in a minute how huge that is. 6 minutes, boom, it separates, falls into hopefully some Indian Ocean or somewhere else. Stage 3 burns liquid hydrogen and oxygen, 200,000 pounds of thrust, not so much, relatively speaking. Burns 3 minutes and it hangs in there. It stays with there's the command module way up there. Crazy. That's awesome. And that launch, that fiery launch that you've all seen, or maybe you should have probably all seen it, is why we had such design issues, because that is an explosion for how many minutes? 2.5 minutes. 2.5 minutes of constant, enormous vibration, explosion, and chaos. Controlled chaos. There's Saturn V laying down. Stage 1, separation. Stage 2, separation. Stage 3. And way up there is the command module. So it's pretty tiny. You see the size of these exhaust ports for the engine. It has a wing, believe it or not, although it's not terrifically valuable, because it's not really guided by the wing, but it does help stabilize it. And you can see by the size of these people, assume that that guy's 6 feet or close to it, that's an 8 foot or 9 foot or whatever diameter exhaust port for the thrusters. Huge. God. Anyway, here's the deal. Finally, we're going to get to something scientific here. Here's the Earth. It's spinning around, and it's moving. Here's the moon over here, spinning around, and it's moving, and the whole thing is moving. It's all moving, and not in 2 dimensions, remember. The orbits are not perfectly flat. They waffle, technically. So you fire out of Cape Canaveral, and you can see the effect of Earth's gravity there. Finally, you break free, and you're out, and that guy stage 1 falls off, stage 2 falls off. You're in the middle here, and you're still riding with stage 3, and you make a little mid-course correction, boom, boom, boom. Now the moon is moving, hopefully toward you, or toward your target. You want to converge there, simultaneously. Big deal secret of the space program is the mathematics of this. And God love these people that figured this out, because It's unbelievably complicated mathematics to figure out when you launch it 7 in the morning from Florida, and the moon's over I don't know, Africa or Antarctica or wherever it could be, and in 8 hours, or whatever, 7 hours, whatever it takes, you're gonna be there when the moon's there. It's not easy. So anyway, you get there, and son of a gun, there's the moon. The moon pulls you in a little bit, you decide you're gonna land, or you orbit actually, and the lunar module goes down and it lands, and then the whole thing is spinning, 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 spinning. And LEM comes back to the spaceship, to the command module, hooks up, the guys crawl through the little tube into the command module, you blast LEM off into deep space, and you use the moon one more time for, as you're orbiting, use it for a slingshot effect, it's called. The gravitational pull, it's a little like crack the whip in a sense. Gravitational pull will get you going, and you break free, and boom, you're out. You make a little correction here, because when you blew off the moon, you weren't exactly pointing to the target, and the target's moving. So you make a mid-course correction, you coast for a while, boom, 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 boom. You make a little correction, and hopefully you land somewhere near the carrier in the Pacific Ocean. Don't ask me how. It's a magic. Here's mission control. You're familiar with this scenario, I'm sure. Here they're looking at the LEM on the moon. Each of these stations has one simple function. Has one function. There are 3, pitch on roll. There's pitch on roll. There's voice communication. There's inter module communication. There's I can't remember all of the things that you're controlling: trajectories, destinations. Those mid-course corrections are made by a combination of things that are found out on the module, which we'll get to in a minute, and things that these guys know. One of these guys is one of the backup astronauts, and if you saw Apollo 13, or maybe next time you see it, you'll watch closer, he is an actual astronaut, so he knows what's happening mentally and physically up there, and the rest of these guys know what's happening electronically or electrically. All right, finally, what the hell did I do? Well, here's a schematic, if you will, of the command module. That's it, it's tiny. 13 feet across right there at its widest point. Where the astronauts sit, it's about 10, and you'll see in a minute. A lot of that's taken up by insulation of the walls. It had to be pretty stable. You must think that through a little bit and find out they're freezing their tuchus off on the back side of the moon, very cold. And on the front side of the moon in the sun, very hot. So you have great temperature variables. These 5 boxes, those 2 and those 3, those were ours. Stabilization and control system was in those 5 boxes. There's a little joystick. Steering wheel, huh? You take it for granted now, didn't exist. Now, with all of that, and the rest of this is communications and gyros, and Honeywell's gyros came back into play with this. Here's some more trivia. If you're going to calibrate a gyro, the Earth is not spinning at the pole, theoretically, or it's approaching 0. At the equator, it's 4,000 miles an hour, roughly. Never mind. You have your own show next week. So anyway, to calibrate something, you want to be at the middle of that variable mess. The 45th parallel runs through the parking lot of Honeywell Aero. 45 degrees, 0 minutes. I love that. I just love stuff. Anyway, all of this super technical stuff, the computers were built at MIT. There weren't even good computer companies at that point in life very much. They used a sextant. So I'd look through an eyepiece, and you'll see this in a movie in a second, on a fixed star, and that was their course. I just think stuff like that's amazing. There's the joystick, and we had to do that, and you'll see why in a minute. Here's what we built, what I built. Little out of focus, but you get the picture. Ironic choice of words. There's a fiberglass, fiberglass is a euphemism a bit for the materials we use, plywood board here, and there's one on the bottom. In between are mylar sheets, and there are some examples of that up here. And the mylar sheets are where the electricity was. Back here would be where the components are, and we'll get a drawing that shows that pretty soon. There are bus bars, they're called. These are aluminum bars that are about 3/32 of an inch by less than an eighth, 32nd about, roughly. Aluminum, straight as can be, rigid, hard aluminum, so it wouldn't flex or bend too badly, or too easily, I should say. And the circuits run this way on both sides of that mylar strip, and then there's a through hole where you weld those together and make a circuit, and you snip off the part you don't want, obviously. Here's a drawing. I remember seeing the drafting room picture. The drawing boards we worked on were about 3 feet by 4 feet, and the drawings we made filled those. A drawing like this would fill that board almost entirely. This is an actual drawing, and it's laying right there. And there's a smaller version of it right there. Black lines are bus bars on this facing side of this mylar. White lines are the bus bars on the bottom side of the mylar. And here are little tabs that are not electrical. They're just there to anchor this thing to the mylar. Where can I find a good picture? There's a weld through where this circuit is welded to this circuit. The reason we couldn't use fiberglass, or printed circuit boards, is because the way printed circuit boards are made, although the technology existed at this point in life, at that enormous vibration at liftoff, the way the circuit is laid onto the fiberglass would come apart. It would literally come apart. The other constraint was this had to be repairable in space. Because we didn't want to leave them out there. Remember the return them safely to Earth phrase. If this thing comes apart, now we had a redundant system. Everything was redundant in this spaceship. In that little spaceship, there were at least two of everything. Anyway, so it had to be repairable in space. They had little welders where if this weld came apart, they could weld it. Fortunately, we didn't have to test that. Little holes, and there's an example of that up here too. These are 1/8" diameter holes, tiny holes. There's an 1/8" diameter hole blown up. You'll notice it's not round. Round is a relative description of a hole. There probably is no round hole. You can see there a little bit of how it's welded, a bus bar to a cable that would go off to a connector. Usually our tolerances were 1/1000th to 5/1000th of an inch. I can't describe to you how close that is to 0. I mean, we had to be on the money. And when we drew that big drawing that I showed you a minute ago that took almost the whole board, it got reduced. And in fact, you'll see the reduced one there to the point where we would put a dimension at the top, and it should be 10 inches or some number of inches on the money, so that when it got reduced to its actual size that it would be in the box, that dimension better be 10 inches, plus or minus 5/1000th of an inch. Tedious. The actual work is not very interesting. All right, here's one of our bread boxes that I showed you earlier. I said there were 5 of them. This is one of them. They're between 12.5 and 20. One of them was 12.5. The other 4 were 20 inches long, because that's all the space they gave us. The boards are here. You can see there's capacitors and resistors and stuff there. One of our matrix boards is there. The bus bars are there. Goes up here, goes to another set of electrical panels. It goes to wires, goes to a connector. This is, I'm sure, power in, electrical power in. The electricity goes wandering all through there. Zippity-doo comes out here and goes to where? It goes to the thrusters, goes to the steering mechanism, the steering device, and it goes to the control displays. So we're doing a lot of things off this. These boxes were made out of one piece and bored out. You see they're joined here, the bottom and the top box, and they're screwed together here. We could not assemble these from pieces because they would come apart. We couldn't cast them because casting is not a very strong process typically, not strong enough as boring these out of one piece. We have several of these kind of things in them to give them rigidity. This is actually, all of this is essentially for rigidity, to keep the metal from flexing. The vibration, I can't, I've said it too many times, but it's an enormous problem with this mission. When this thing, when these 5 boxes, these are bolted to the Space Command module, you've got to remember. And when that thing starts to rattle, these things cannot, nor can the contents. So here's a command module. This is an actual command module. 13 feet at its outside where the guys sit, 10-ish. And there's what you're contending with for taking up some of the interior room. So you wind up with about 8 feet, 3 guys in essentially what would be 2 snowmobile suits each, sitting shoulder to shoulder, and that's it. 10 days. And all of the body functions exist. All of the body functions. And there's no gravity. I'm gonna work on that. These are 2 thrusters here, there's 2 there, there's a couple there, there's a couple up there. These are windows, the observation windows. These thrusters were fired, obviously, for some period of time, and they're burnt. They burned the shell a little bit. These handles are for the frogmen in the Navy to grab and right this thing if it doesn't land properly in its inner tube, lifeboat. Another window's up here, I think. Those are thrusters up there too. Okay, I thought that was a sextant window, but it isn't. This was obviously a used command module. All right, here's a little rundown. This is the command module, tiny, very small. This is the equivalent, I would equate it to 3 guys in these big snowmobile suits and big gloves driving for 10 days. You can't drive for 10 days very well, but without getting out, without standing up very much, in a van, in a big truck maybe. I don't. Claustrophobia would only be one of the issues. This thing turned out to be not so useful. This is all stuff, fuel, and whatever in the service module. The engine for the last part of this gizmo sitting there with the low fuel cylinders there. And back here is LEM, lunar module, sitting right there, and some electronics and thrust, fuel thrust for this stage 3. Stage 3 is back here. That's the classic picture we've all seen. This black thing is the service module, that's the command module, I mean. That's where the 3 guys are. This is all stuff. This is LEM, and they're gonna dock. They're gonna come right into the nose. They get close, they contact, and it electronically sucks them right in. So because when they're docked up, that better not leak, or they go to space. These are the spacesuit. This is spacesuit. You can look at that all you want. This is kind of a good idea. You can see their shoulders are just about touching. The 3rd guy over here you can't quite see. And this guy, I don't know who it is anymore, but I think it's Scott, is demonstrating the size of these gloves. This suit, when you saw the guys on the moon, they kind of hopped. That's because you can't bend your legs in this thing. If you try to take a step forward, you'll just fall. This is the clumsiest thing you could ever imagine. And they're working desperately to get a better spacesuit. Because if they want to go somewhere else, it won't happen. All right. It's time to watch this footage if I can make it work. If I can remember how to work my computer. Which is, of course, something I'm not terrifically apt at, because the last time I did one of these slideshows, I did it with 35 millimeter slides and an overhead projector. That's not it. That's not it. That's not it. Where'd it go? All right, this page, I don't want that page, so I don't care. Apollo stuff, technical talk. We already tried Glenn Miller and he didn't work, so we'll see if James Burke will work. James, this is a file footage from the BBC. We're doing all right, I think. Maybe. Oh, I love technology. I liked it better when you just said, roll the projector, Aaron. Anyway, if this works, it'll be worth it. You know James Burke from the BBC, probably. Ironically, the BBC did a nicer program on this than I could find anywhere else. This page can't be displayed. Isn't that great? I don't care. I want to see it. Well, assuming it comes up, I won't have to say this, but he takes you actually into the space command, into the Apollo command module, and shows you with the middle seat removed how little space you wind up with. And believe me, now 10 feet, I don't know, this is probably about 10 feet, or something close to that. Seat here, seat here, seat here, and these are big seats, chairs, and they lay back. Of course, you don't, in space you're not laying because there is no up or down. I guess it isn't going to play. It's very unfortunate because it would demonstrate all of what I want to show you. So I'm going to fight it, which is my nature. I hate things that don't work. Oh well, maybe I'm not going to fight it. All right, forget it. Not worth it. I'm not going to take up your time trying to make something happen that ain't going to happen. So anyway, it shows you how tight this is, and it gets it. There's one place where you can stand up in here, and that's where in the middle seat, there's a little room in front, and that's where the navigator can stand, and it's about this big. And he looks through the sextant to get his fix on a star. Once he's fixed on a star, he hits a button. That position is locked in to the computers, the onboard computers. And the ship then has a good set of data, GPS essentially, if you want to think of it that way, to get to where they want to go. There's no highways. There's nothing. Okay, aside from size, and the fact that none of this was known information, the other constraints, of course, were the dynamic duo of time and money. We had 2 years to design this stabilization control system, the SCS, and we had to come in on budget. Honeywell did come in on budget. The whole Apollo program started out at $7 billion, a little low. They revised it to $20 billion. This is in 60s money. Finally ended up at $24 billion. The Saturn V rocket that you saw is $9 billion, and mission control that I showed you was $7 billion. That's about $40 billion, roughly. And in 2005, which was the last conversion I could find, that's about $170 billion. You could not do this today. The government, our government, would never pass anything like this today. They can't pass anything to begin with. They would never appropriate this kind of money for science research, and that's what this was. Actually, it was defense research. Star Wars and all of that evolved out of this, but a terrific amount of science came out of this as well. The interstate highway system and the space program both came out of the 50s and 60s, and neither, I'm convinced in my older cynical years, that neither would be allowed today. Just wouldn't happen. But I'm a cynic. The movie Apollo 13, terrific movie if you get a chance. My wife goes in the other room when it comes on. The actors actually, because I've seen it 7 or 8 times, actually went through astronaut training, ironically. This film was produced by Ron Howard, Opie. Ironic, huh? Long ways from Mayville to the moon. All original film. He used no NASA film. They built exact replicas. The Len is a lifeboat. They use it. I mentioned that. That was always the plan. Everything's very realistic. God, it's just terrific. To get the weightlessness films and to practice weightlessness on Earth, which the astronauts had to do, you go in a KC-135 aircraft and you go way in the sky and then you drop. I don't know why you do this, but you do this. For 23 seconds, that's about as much as you get, and then you better put the engines back on because you're gonna die. And then while they're doing, and take everything out of this plane and pad the perimeter and the surfaces of it, and because when you go back and fire the engines again, you're gonna fall. The reason you're weightless is because you're falling faster than 32 feet per second, which is gravity. Plane's falling, it's a forced dive, it's falling faster than gravity. So you float. And that's an experience not a lot of people have had. Jim Lovell, I was right, Jim Lovell was one of the astronauts on Apollo 13. He wrote a book, which the library has right over here, about that. Now I just heard, literally, last week, we were planning 6 moon missions, none of which are manned. But now we can do things robotically that we couldn't do, of course, in the 60s. They're all moon missions, they're all unmanned, and I think they're imminent. NASA is not dead, as people think. Actually, NASA is about 1 cent of every tax dollar. Another piece of trivia for you. So, what's it all about, Alfie? People ask me this all the time. So what? So what? We went to the moon. Well, we got a lot out of it. We got a lot out of it. This list is, believe me, a long ways from complete. We advanced, if not instituted or invented, all of this and much, much more. Fire-resistant coatings, things that seem to be kind of innocuous, but have saved lives here on Earth. Better golf balls. I mean, gee whiz, who doesn't need better golf balls? But really, there was a huge growth in this, both in academia and the workplace. And that's very important to us as a country. The lasting gain that I think we got out of it is that we found out we're on a little blue marble in a vast void. This is it, folks. We consume this thing, we're done. It's over. There's no lines from here to anywhere, at least not yet. So that's my take on it. Earthrise is the name of this photo. It's also the name of a book I have here. It's a terrific adventure. I was incredibly lucky to be found, first of all, nominated and held captive by Honeywell, and the top secret clearance. Who knows what that led to as far as my military life. I think it's an incredible journey. It's a great part of America's history. Now I can't think of the scientist's name on PBS, the astrophysicist, big guy. Can't think of his name. He's going to speak at Drake University real soon. Anyway, he says the biggest thing that he got out of this, and he was a kid when this was happening, was the hope. This gave America hope. It gave you vision. It projected you into another dimension of thinking. And we don't have anything like that right now. And I think we need something to make us feel like, as a human race, there's more to life than this. And I don't mean that to be cynical, I just think we have the potential to do much better, and we should. And it's our nature, I think. It's like crossing the ocean to find a new world, or moving to a new state, or whatever. It's in our DNA. Anyway, that's all I got. There's stuff up here if you want to look. I'll answer questions. Thank you.
How big are the rotors in those gyros that Honeywell built?
How big are the rotors in the gyros that Honeywell built? For the space program?
Yeah.
Let me think. If I can, I've seen them. I'm trying to picture the scale of them. They're not big. They're less than an inch.
Okay.
3/4 of an inch, probably, something in that range. I didn't have a lot to do with the gyros part of it, but they're in that ballpark of 3/4 of an inch. They're small, but they're really accurate. And they float in a liquid that is, I can't remember, but they float in liquid so they're not constrained. A very friendly viscosity. Any other questions? Yes?
Before that took off, that photo you had was laying down horizontal.
Say what?
The Saturn is
Yep.
laying down horizontal
Yep.
with those pictures. And how did they get that thing raised vertically?
Well, actually, the one that you saw laid down, the question is the Saturn V rocket laying down, how did it get raised? Because it's enormously tall. The rocket that one was actually laid down. They build them vertically in the vertical assembly building. That's the name of it. You know, and it's built on railroad tracks. And you may remember seeing this. They go like 1 mile a minute, or an hour, I mean. They slowly bring, and the rocket is assembled in this building. The building is that tall. So it's built in those stages, assembled in those stages. The church, built in other stages, they crane it up to and secure it. And then they build the next stage, crane it up and secure it. Then they put, on top of it, then they put the command module and that funny escape thing, which didn't work, and whatever else they needed. But it's built in the vertical assembly building, or assembled in the vertical assembly, and it comes out on railroad tracks out to the launch pad. Railroad tracks go right into that big enormous machine that catches it and secures it, because Florida's windy sometimes. And when they launch, you see those things explode away, those arms that are holding it. They literally explode away. Joanne is giving me the hook. So if you have any questions, keep them to yourself. I'm out of information, so I'm going to make up anything if you ask me anything.
We'll bring you back down to earth. Is this on? Can you hear me?
If you're ever asked
We'll
to
bring you
speak
down.
here, don't do it.
We'll bring you back down to earth
Yeah.
with a little reminder
Thank
of our
you.
thanks. Flowers on Fourth is joining us, and thanking you very much for absolutely fascinating. It's marvelous. We lived through this. It's wonderful to see what we were really hearing about. Some of the things that you talked about were things I remember distinctly on.
Yeah.
Thank you very much for
Yeah,
our
we used to
wonderful
get
hour
up
and a half.
Used to get up at 5 o'clock and watch the launches and stuff.
Yes,
It was a big deal.
thank you very much.
Thank you. I appreciate the opportunity to relive a couple of years of my past. It was fun to put together. Thanks.
I want to remind you that next week, a real professor will be here. Earl Clodfelder will be talking about the beginning of the scientific experiment. And I've asked him to say just a couple of words about that so that you can be all ready for next week. Earl?
Well, this will be quite a time change, because next week I want to go back to the 17th century. In the 17th century, scientific societies began to be formed, scientific journals were introduced. I want to look particularly at the Royal Society of London, which was chartered in 1662 and began publishing its journal called the Philosophical Transactions in 1665. There were no established rules about what should be in a scientific journal. Part of the members of the Royal Society were amateurs. They really weren't professional scientists. They were not even trained very much in science. And apparently in the first year, anything somebody submitted was published. Some very odd articles were published. And I think you'll get a lot of pleasure out of seeing some of the early scientific, in quotes, articles published in that journal. So I'm going to be looking at the beginning of the scientific enterprise, the formation of one of the most important societies of scientists, and the publication of one of the most prestigious and continuing journals in science. Back to the 17th century from the 21st.
I wonder what Jim could have done with the 17th century. Please take time to look at some of the things that Jim has up here, and then we'll plan to see you next week. Thank you for sharing your morning with us.